So hello everyone. Today we will be going to implement a multiplexer circuit in Synopsys custom compiler. So multiplexer allow us to choose one input from the transmission to the output using n is equal to 2 raised to m control bits, right? For so it's n is to 1, right? One output, many inputs, and m is the control bit, right? So we can have 2 is to 1 multiplexer, 4 is to 1, and 8 is to 1, like this, right? We will be implementing 2 is to 1 multiplexer using n-pass transistor logic. So over here, I0 and I1 are the inputs, F is the output, and S0 is the control or the select pin. So this is your truth table. If S0 is 0, your output will be I0, and if S0 is 1, your output will be 1, I1, right? And that's the expression S0 bar I0, F is equal to F0 bar I0 plus S0 I1. So this means that S equal to 0 gives us I0 and S equal to 1 gives us I1. And this is the n-pass transistor circuit which we will be implementing in custom compiler. Okay, so let's start. Let me open the custom compiler tool. And now let me open the circuit. Let me keep it open. So we'll start quickly building the 2 is to 1 multiplexer using NMOS pass transistor logic. So we'll open the library manager, and here you can create your new library. So let me name it as ISD MUX 2 1. Okay, I can click on OK. And once my library is created, I'll need to create cells inside that. Fine. So you click on this MUX 2 is to 1, and then I have to create a cell over here. Okay, the cell name I can name it as ISD MUX using NMOS. Okay, I'll click on OK, and then I'll select this cell and I'll go to view. I'll just extend it a little more. I'll go to new, and then I'll go to view name. That will be schematic, and then I'll press OK. Fine. Your schematic screen has appeared. Now next is we have to select the instances. So from here we have to select the library as 28 nanometer. The cell will be NMOS 4T. We can type over here also NMOS 4T. Okay, we can keep the length is around 30 30 nanometer, and the width is around 100 nanometer. So let's keep it by default. So we will add this. We can change the orientation like this. So we'll keep one like this, and other one will be like this. Correct. And now we will join them together. So let us join them together. Yeah. So these two can be joined together with a wire. First of all, let me just take it away from the axis. So I'll use this move button and take it away from the axis. Yeah, like this. And now I'll be connecting them with a wire. So this one will be connecting to here. With a wire. Okay, let us quickly do the connections. Yeah. So also remember that the body terminal of NMOS has to be connected to the ground. Now over here, this is my output pin. This is my output, right? And this I0 and I1 are my two inputs. Correct? And then S0 and S0 bar are my select line. S0 and S0 bar. So if you generate a signal S0, how will you create S0 bar? By giving it to a inverter, right? So we can generate the signals with the help of inverter. So let's do that very quickly. So I will label the nodes also. This I will label it as output. So we can label the wire by right clicking add wire name. So I can name it as output, and this I can label it as I0. Sorry for that. I can name it as I0, and this I'll name it as I1. Fine, this is I0 and I1, and this will be S0 and S1 that we will be connecting it over here now with the help of an inverter. So again, you'll go over here and select NMOS. So NMOS is selected now. We can also select the PMOS for the inverter part. So let me select a PMOS transistor and keep it over here. Yeah. So PMOS transistor is connected. Now I'll do the connections for the CMOS inverter with the help of wire. The connections have been made. Now remember, for a substrate for a body terminal of a PMOS, it will be connected to VDD, and the body terminal for a NMOS will be connected to the ground. So I have quickly made the connections. This will be input, and here it will be my output, S0 bar. Right? Let us name it now. This will be S0, and over here we will have S0 bar. Fine. Now let's check the supply connections. Supply also we have to connect, right? So let us use the wire again and complete the connections. So I'll use the wire over here and I connect to the source terminal of PMOS transistor. The body terminal also will be connected to the source terminal. So I'll take the wire from here and I connect it to the source terminal for a PMOS transistor. For an NMOS transistor, the wiring will be like this. The body terminal will be connected to the ground. I'll do the the wiring is completed now for the CMOS inverter, right? And here this I will name it as VDD, and this will be VSS. Okay, fine. Now what we will do is we will name this also as S0 and S0 bar. So let's quickly do that. Yeah. So right click. I right click over here. This I'll call it as S0 on the wire. No need for connection, but we can easily do it. Right click on the wire, add wire name, and here I can give it as S0. You have to give the same name, S0. Yeah, and above I'll give it as S0 bar. Yeah, this is I0, I1, S0 bar, S0, out, and this is VDD, S0, S0 bar, right? Now I have to give the supply. I mean, I also have to give the body terminal of NMOS transistor towards the ground. Ground will be treated as VSS over here. Yeah, so this is actually VSS. Yeah, and this NMOS transistor also, its body terminal has to be connected to the, okay, the body terminal connection is not proper. Let me add it with the wire, and then right click, add wire name, VSS. Okay, so our schematic is complete. Now we have to add the pins. Make sure that you save the schematic. So for adding the pins, we have to click over here, right? And we have to write the name. So this is I0, pin I0 input type. So we'll add it over here. Okay. And similarly, we will have another input, which is I1. And we will add it over here, another input pin. Then we have another input pin S0. So this is to check this is the select pin. So here I will be connecting it like this. Yeah. And we will have a supply and the VSS pin and the output pin also. So let's start with the supply. So for supply pin, we will change the orientation and we'll call this as VDD and we'll connect over here. Right? We'll do the connections now for the I0 pin. I0 pin will be connected over here and I1 will be connected over here. Fine. And then we'll also define the VSS pin over here like this. Okay, this VSS pin I have to name it over here. Then only it will take. Yeah. So VSS is also added. Now I'll be connecting them together with the help of wire. These are the supply pins which has to be connected in order for the CMOS inverter to work. Yeah. So if you give a CMOS inverter S0, it will produce S0 bar. That is for sure. So let me connect this S0 pin to S0 wire. Now only one pin is left, which is output. So once you connect the pin, your type will be output. You have to select output type. And now we can rotate it as desired and connect it over here. We have to call it as output. Okay. And I'll connect it with a wire. So this is the schematic which we have created so far. Let me save the design. This is for the 2:1 multiplexer using NMOS pass transistor logic. Fine. So this is your design. And now this is my schematic which I have created just now. Now I have to convert it into symbolic representation. So what I will do is I'll go to design, then I'll go to new cell, then from cell view, your symbol editor will be there. Then I'll click on OK. Fine, a new symbol will be created. Here I can slightly zoom out a little. I push this symbol away from the axis so that there is no problem in viewing. And now I'll be maximizing it. So this is the symbol which is getting created. Let me go to the full screen mode so that it's clearly visible. Yeah, I have to delete these terms, extra terms from here. Actually, S0 bar also it's there, but it's fine. S0 bar has to be connected. It's already connected. Yeah. So let me delete this. You have to delete them. inside also we have to delete them. They're not required. And now I have to, this is the symbol which is created. I can change the shape of the symbol using this, but let's keep it this way only, right? We have inputs I0 and I1. What I can do is I can separate them out a little. Okay, let me just, it's slightly slow. Let me go out of the full screen. And then continue with the design. Here it is, right? So here I will have a select pin S0. Your VDD will come, output will also come over here. So actually let me select this S0 pin here only. So I will click on this. I will move this pin away and keep it over here. Okay. Output pin, I have to add it over here so that inputs over here, output over here. So again, I'll be selecting this move option to select this pin and bring it over here. Okay. And then I'll orient this VSS so that it's aligned with VDD. I'll slightly move towards the center. Yeah, that is fine now. Next is I will create a space between I1, I0. Let me connect it here only. Yeah. And then you have to select this S0. I can rotate it with R and I can place it over here. Okay, this is my S0. And finally, my output has to be connected. So I can select this. I can click on R. And finally, I'll place it over here. Yeah, it's been added. Let me orient I1 properly. Slightly up. Yeah. So now it's done. Also S0 slightly up. Yeah. So this is my symbol for my 2:1 multiplexer. I have to give name also here. Right. So what I will name it as, I'll right click, edit. I can name it as ISD underscore MUX underscore NMOS. Okay, because we are using N-pass transistor. So this name, I will drag it inside the symbol. So this becomes the symbol of a 2:1 multiplexer now. Okay, VDD, VSS, S0 and output, right? We require VDD and VSS for the inverter, right? Now, let us save this. Now that we have created the schematic, this was the schematic for 2:1 multiplexer, and that's the symbol. Now we'll close this board. Now we'll have to create a test bench. So for creating a test bench, you have to right click over here, create a new cell. We can call it as cell name as Testbench TB and click on OK. So MUX NMOS Testbench. I'll click over here, go to view, right click, go to new, and from here I'll select the schematic. View name will be schematic. So view name is schematic. I'll click on OK. So a new schematic will appear wherein I will be adding the test bench, the symbolic representation of 2:1 multiplexer, which we have created. Yeah, so this is the one. This is the test bench schematic, which we will be adding our symbol of 2:1 multiplexer, which we have created just now. So click on add instances. It will take some time. And here you have to add the library which you have created. Okay, so click over here and add the library 2:1 multiplexer. We have to add the cell. Which cell we have created? MUX and MOS. So as soon as you connect over here, the symbol will come. You drag it. Right. So this symbol is appearing onto the screen. Now we'll observe the output, right? Whenever S0 is 0, it will give I1 at the output, and whenever S0 is 1, it will give I1 at the output. Okay, I0 and I0. Now we have to apply the supply pins. So we have to add instances. So for adding the supply pins, we have to go to analog lib library. So from here, I will select analog lib, and here the cell name will be first of all VDC. I'll be selecting VDC. Okay, it's taking some time. Let me directly type over here VDC. We select the supply as VDC. Now, since we are going, on a 28 nanometer node, we can select an extremely low voltage. So here, let's say that we add around 1.2 volt. Okay, it should work even at around 1.2 volt voltages. Okay, and then I'll place this. I can rotate R. I can place this over here, the VDC supply. Fine. So the VDC is added. Now I have to add the ground. Ground I will add it later. Now I'll add the pulses. So again, I'll go to add instances. So yeah, it's loading. So please be patient. Now from the cell, we have to select V pulse. So I can double click on this. I can directly add V pulse from here. I can select V pulse, right? I have to select it for I0, I1 and S0, right? So let this voltage go from 0 to 1.2. Delay time will be 0 initially. Then rise time will be 0.1 nanosecond. Fall time 0.1 nanosecond. Pulse width I can give it as 5 nanoseconds, and period will be around 10 nanoseconds, right? So this pulse I will add it over here. Yeah. So now I can adjust the over here, right? Now I have to select another pulse for I1, right? Here the voltage will be 1.2 volt, 0 to 1.2 volt. Delay time I can give it around let's say 2 nanoseconds. Earlier we have not given the delay. Now we are giving the delay of 2 nanoseconds. Rise time will be 0.1 nanoseconds. Fall time also same, 0.1 nanoseconds. Pulse width will be 5 nanoseconds, and period will be 10 nanoseconds. Okay. Here, let me change this delay time to 2.2. Okay, by default, it has come 2.2 seconds. It has to be nanoseconds. 2.2 nanoseconds. Yeah, I'll place this over here and escape. So this is my I0. I'll be using the labeling technique, and then I have to create S0, right? So again, I'll go to add instances. Pulse will be added. Again, the duration will be, the voltage will be 1.2 volt. Delay time will be, let us give the delay time as 6 nanoseconds. Rise time will be 0.1 nanosecond. Then fall time will be, let's say, 0.1 nanosecond. Pulse width, it will be slightly greater than the earlier one. So we can give a pulse width of around 10 nanoseconds. Let's say not 10, 7 nanoseconds. And the period will be around 14 nanoseconds. Okay. So this pulse also I will add it over here. Yeah. Okay. Sorry for that. Yeah. This one. Okay. Fine. There are two. I think two are added. So I have to delete one from there. Two sources are added by mistake. So I have to click on delete. Fine. It's sorted out. Now I'll drag this source over here. Yeah. Now I can add a label, right? And I'll have to add the ground also properly. So let me just maximize the screen now so that I can get more workspace to work around. Yeah, fine. So let me click over here. Now I'll move around this pulses a little bit away. This pulse also over here. It's slightly slow today, the server for custom compiler. That is why it is lagging a bit. But you have to be patient. Here we will add the pins. Now we can go to full screen. That is not a problem. So that we can have a better view of it. Now we'll add another wire from here to here. Another wire from here to here. Okay. Then I will be connecting it this way and directly connecting to the ground. Okay, ground we will connect it very soon. No problem with that. This I can connect it like this over here. Right now I have to label this. This will be add wire I0. Okay, it has to be I0. Yeah, I0 has been added as the label. Next label will be I1. And this label will be S0. I'll right click on the wire, add wire name. Okay, it's slightly delayed, but it will work. Right click on the wire, add wire name, that is S0. Okay, fine. This is done. Now we will label the sources. So this source will label it as I0. So this is my I0. This next source I will label it as I1. This is I1. Okay, I have to change the label. I1. Okay, now it's proper. And this lower one, pulse source, I will label it as S0. Right click on the wire, add wire name S0. Okay, now is the time to add the ground. So I'll again go to the instances, double click on the pulse. I in fact cancel it and type GND, that is ground. So once you select that, the ground will appear. We can add it onto the schematic. And we can add over here also. Later on, we can adjust it. Yeah. Now the ground is added. Now we have to make the connections. Okay. Fine. Now let me push this slightly down. Yeah. So this is done. Now I'll be adding the grounds one by one. So let me select this ground also. I'll adding it properly in a symmetric fashion. Okay, fine. Let me adjust the ground properly. Okay, let me go back and select the ground and bring it over here. And then this ground is already connected. Let me add this ground properly below the terminal. Yeah, and I'll join them with the wire now. I'll connect them with a wire. This you can rotate also. I can pull it down. Yeah, And actually one more grounder will be required. So I'll go over here and add a ground here also. Okay, fine. Now let me connect the wires quickly so that the circuit is complete. Here also, let me add the wire. And finally, VSS also is connected to the ground with a wire. And finally, the VDD supply source also is connected to the ground. Okay, I guess it should be 1.2 volt, right? It's 1.2 volt, not 12. Read it as 1.2 volt. We have applied. Fine. And now we are ready to simulate. Let's check for any errors. So there is a check and save button. Let's see if it gives any errors. It will give you just one warning that output node is open circuit is floating. That's absolutely fine. We can check the output. We can drive a capacitive load over there. So what we can do is, if you want, you can connect a capacitor. So in the cell, you can type cap. Okay, you can add this capacitive load at the output over here and connect it with a wire so that that error won't come. Now I have to connect it with a wire. Okay, and this other end will be going to the ground. So here I'll be connecting to the ground. So now if you simulate again, the error won't come. Okay, so I think this connection is not made properly. So I'll just maximize a little and then check it minutely where the connection is not connected. Okay, fine. Here we have not labeled the node. We'll label it as, let us call it as out. Yeah. So now let's simulate again and check for any errors. So we have saved it. We are waiting for the console to show us any errors if they are there. Yeah, it's showing that still the capacitor IO pin is floating. Output pin output of instance I0 is floating. There are two warnings, no errors. So it's absolutely fine to keep it open also. No problem. So we can remove this capacitor. Okay, sorry for that. We can remove this capacitor, no problem. It won't make a, okay, sorry for this. Yeah. What we can do is we can right click and delete this, not a problem. This wire is extra. We can delete the wire. Yeah. And then we can simulate it further. No problem with that. Without capacitor also, it will work. Let me delete this wire. I'll right click and delete the wire. Okay, so now our test bench is created. Now we'll start with the simulation. Let me just check it out. Okay, so let me put it back on the, remove from the full screen mode. Yeah, so we have created this circuit. I'm in the test bench. Let me show it to you. This is here 2:1 multiplexer. And these are the inputs I0, I1 and S0 is the select line, right? And now we are ready to simulate the circuit. So for simulation, we have to go to tools. We have to click on prime wave. Okay. So your prime wave, the test bench will appear. In that, we have to add the model file. So in a model file, we have to include the part. So that I will get it from the library manager. Right click on this library, copy the part and copy it over here. Add it like this. I think at different computers, if you have installed in the computer, it will be located in a drive, right? So see to it where it is located. Here next, I will search for the model file. So that will be in the HSpice folder. So here it is. I'll click on open. Yeah, the section will be TT. So select TT and click on OK. Fine. Now that we have defined the test suite, I mean the test bench, here it is. Let me just select that. Yeah. So this is my test bench and I'll go to the analysis. I'll double click on the analysis part. Okay, it's loading actually. Yeah, the analysis window has opened. Here we are going to do transient analysis. So step size will be 1 nanosecond. Stop time, we can give it around 30 nanoseconds. That's fine, absolutely fine. And then click on OK. Fine. Now after that, we have to go to expressions over here and click over here so that you can pick from the design which value you want to plot. So I wish to plot I0. So automatically the color will be assigned. Next, I wish to plot I1. And next is I wish to plot output, V out. I mean output, right? Also, I wish to plot S0. Okay, fine. Now all the things are ready. We have to just click on simulate. Simulate, netlist and run. So it will take 5 to 10 seconds for the, the input output waveforms to appear onto the screen. So just wait, it will soon appear. Yeah. So now what we will do is we will just, let me adjust the window. Maximize this thing. Then I will be ungrouping it. I want to view output also. So let's see what went wrong. Output also should be visible. Let me close this. Okay, there is an error over here. What's the error? Let us check in the console. What's the error? Okay. It exited normally. So what I will do is I'll close this console. I'll save this test bench. Let me close this test bench and open it again. Sometimes that solves the problem. So let me save it in the name as test MUX. Test underscore MUX and click on OK. Fine. So test bench is saved. So now what we can do is we can go over here, library manager. We can go to the MUX 2:1, select the test bench and here test MUX. That will directly open the test bench, right? And now we have to simulate netlist and run. Click on netlist and run. So in 5 to 10 seconds, your output will come. So there is a error evaluating the output value. So we have to see what has to be done. So either we can connect the, we can go to the test bench. Let us see what is the problem. Rest all the inputs are coming properly, only the output it's not proper. So yeah, we will close this test bench and again go to the MUX schematic to view if there is any error. Yeah. So here is the output, correct? That output is here. And yeah, everything is proper over here. Then let me go to the symbolic representation. I mean, let me directly go to the test bench. I think we have to have a capacitive load at the output. Then only it will behave properly. I guess so. So let me go to the test bench and I'll go to the schematic. I have to connect a capacitive load at the output, right? So let's do that. I think, okay. I got it. I got it. So let me close the test bench schematic. I got the problem where it is. It's in the symbol. So you see this, this is wrong. This has to be connected over here, right? So we have to move it like this out of here. Maybe we can, okay, sorry for that. Maybe we can select it now and then rotate it. So this red color part has to be connected over here. Okay. Now we have done some changes in the symbol. It has to be reflected in the schematic also. So I'll go to update cell view. So that will update in the schematic also on completion. I'll click on OK. So wherever we have used this symbol, it will automatically update it. So now it won't give a problem. So I click on OK and apply. Okay, it's taking some time. I'll click on OK. Okay, fine. So I've saved the design. And now let me try again. Update cell. Yeah, it won't matter much to the destination cell, that is schematic. It will automatically, it was a problem in the symbol. So we have updated it. Now let me close it. Now let me go to the test bench. Over here, schematic. Let me open and check. Yeah, now it's proper. Now it won't give any error. So let me start with the, it's already saved, right? Yeah. So let me close this and go to the test bench directly. And here we are directly plotting the, I mean, we have selected I1, I0, output and S0. So now we'll go to simulation, netlist and run. Now it will give you proper output. It should give you proper output. It will take 5 to 10 seconds to complete. Yeah, there are no errors, fortunately. And yeah, you will get the plots very soon. Yeah, here are the plots. Let me just maximize the plots over here. Fine. And let me ungroup them. And let me observe the output now. So that's how the output will look like, correct? And why it is so, we will also explain now. Because it's an N-pass transistor, because we are using an N-pass transistor, it's not a very good, it's not a very good transmitter of logic 1. So logic 1 will be VDD minus VTH. Okay, it will be VDD minus VTH value. Correct. That's why we can see some, we are getting less than VDD. VDD is 1.2 volt and we are getting around at 1 volt value. Right. Now let us confirm this output behavior. So let me turn off the grid. Yeah. So let us check it out, the functionality. So whenever S0 is 0, so S0 is 0 from year to year. Okay, your output will be I1, your output will be I0. So this is your I0, so red color one, so output is also following that. Only thing is, it won't, it is not reaching up to the level, that is 1.2 volt, it's not reaching, it's around short. So maybe the threshold voltage of the MOSFET is around 0.2 or 0.3. That's why it's not going over here. So that functionality is correct. Whenever S0 is 0, I0 is at the output. That is correct. Next is uh, when your this thing S0 is 1, your output will be following I1. At output, you'll get I1. So here it is I1 is going down and again going up. So it's perfectly behaving well. And then whenever S0 is again 0, I1 will I0 will continue. So from here I0 takes over, and that is what you get. So it perfectly behaves as a 2:1 multiplexer. Only thing is that the limitation of this circuit is that here the NPAS transistor is used, NMOS transistors. And NMOS transistors are strong transmitter of logic 0, but a weak transmitter of logic 1. And here we are talking about the voltage levels of 1.2 volt. So definitely the voltages are small. So the output, maximum output value will be VDD minus VTH. So that's why you don't get up till VDD value. And that is what you get output over here. It's perfectly behaving fine. It's working as a 2:1 multiplexer, right? So that is how you build a 2:1 multiplexer using a in custom compiler in Synopsys tool. So let me close this. Let me close the output waveform, the Synopsys tool. And let me show you the netlist for it. So netlist will be available over here. You'll go to simulation, netlist. You can display the netlist over here. Okay. So this is the netlist which we have created internally. We have created a sub circuit, and these are the pulses which we have created over here. Okay. So that is the netlist which we have given the name of the cell as multiplexer 2:1, and inside that library as 2:1. Then cell name was MUX NMOS Testbench, right? So now we can close it, and then we can close the Testbench from here, and we can save the state so that next time when we open, we can directly start from here. We can save the state, save the changes prior to closing. Yes, we'll click on yes, save it. Fine. So this simple example demonstrates the working of a 2:1 multiplexer. Yeah, the save is clicked, but I think it's slow. The server is slow. That's why it's taking some time. Yeah, it is saved. Now I'll close it. So yeah, that's the end of it. I mean, 2:1 multiplexer. That's how we will implement using custom compiler tool in Synopsys. And I want to acknowledge, IIT Hyderabad hackathon, analog IC design hackathon, and the Synopsys, Synopsys tool, which they have provided via the cloud-based, server. So that's the server which we are using over here using the custom compiler. So we have started with creating a schematic view for a 2:1 multiplexer. We have created that. Then we created a symbol for it. Okay. And this was the symbol for 2:1 multiplexer. And then we created a test bench wherein we tested up by applying the circuit, applying the various input pulses over here. Okay. And we got the output as desired, along with one limitation that the NMOS will not reach up till VDC level of 1.2 volt, because it's not a good transmitter of logic 1. Logic 1, it will always be lesser than VDD minus VTH value, the threshold voltage value. Okay. So yeah, that's all from my side. Right. Again, I want to acknowledge a cloud-based analog IC hackathon, which provided us with the custom compiler tool in the cloud platform. So yeah, that's it from my side. And thank you for joining.